Hi, today I'll be going through questions 1 through 10 of F equals MA 2024, and we'll start with the first one. So it's about an arrow passing through two hoops, both at height h above the ground. So I'll draw this, h. They're both at height h. One thing you notice is that the x component doesn't actually matter. All that matters is the height and like when it hits the ground. So I'll relabel this axis with t. Here will be height h. Here will be time equals 1, here is time equals 2, and by symmetry of the parabola, we know this is time equals 3. So now we know that the arrow falls to the ground in 3 seconds, and this is a pretty basic problem that we solve. I actually prefer the version where we look at the 1.5 second mark, and that's when velocity equals 0. So then using our kinematic equation, 0 equals v naught plus uh, at. Acceleration is equal to negative 10 meters per second, and time is equal to 1.5, so it's v naught minus 10 times 1.5. So we have v naught equals 15. And just to be clear, our v naught is all of the velocity in the y direction because the x direction doesn't actually matter. Now, we've got to see the height that it reaches after 1 second. So so h equals, using the other kinematic equation, v naught t plus 1/2 at squared. We know a is equal to negative 10, so I'll simplify it to minus 5t squared. T is just 1, so it's equal to 15, which is v naught, minus 5 equals 10. Great, we've solved the first one. Question 2. Okay, this one's about a circular horizontal room, and we're trying to find the angular velocity, omega, when the rider's feet first lift off the floor. So here, I'll draw the triangle for the room. And so rider's feet first lift off the floor when all of the forces are sort of balanced. Here can be the rider, just a block free body diagram. So there's the force of gravity going down. There's the normal force going in that direction. And the final force, well, actually, these should add up to, when I put them together, Fn plus Fg should add up to the omega squared r that we're given. Now, yes, technically the units don't check out, but we're just going to look at these as forces per unit mass. So like Fg is equal to, checking the answer choices, there's no g in them. So I'll just simplify this to 10. Omega squared r is down here. If we remember, this angle here will be what happens if we continue this line. And this is 30 degrees because we know that this is 30, so this is 60. So now we've got a 30, 60, 90 triangle. This is 10, so omega squared r equals 10 root 3. Just solving the triangles. R equals 5. So omega squared equals 10 root 3 over 5, which is 2 root 3. Now I'm going to calculate the square root of 2 root 3 using my calculator. It's 1.8612. So I think that means it's 1.9. And great, we've now solved two questions. Now, a simple bridge is made up of 5 thin rods rigidly connected to 4 vertices. So no friction on the ground. The idea is it has to carry this force. Each of them is experiencing tension or compression. Now, I assume you know what compression is. It means that it's sort of being, like, if we got a rod, it's sort of being pressed inward. And I'll notate it like this. And from that, you can infer that tension is being pulled outward, like that. Now let's evaluate each of them. BC. Is this being pulled outward or inward? Um, so if I imagine it were a little stretchy, what would happen is F, like the force would sort of pull it inwards or downwards, and it would like fall if BC were more stretchy, and then BC would be stretched out. So not being compressed, it's being like uh tense. It's in tension. Similarly, you can see that CD is also in tension, and AC, that's directly holding up the force by like being tense. So that means that it is being pulled out. Like you can just imagine if AC were more stretchy, it would like stretch out. Now what about AB? If AB were like sort of bendy, I think it would actually go inwards because you can imagine like it would um it, the it would sort of collapse in on itself. And same for AD. It's being compressed inward because if it were stretchy, it would collapse in on itself. So we have tension for the BC, CD, and AC. That means the vertical rod and the horizontal rods are in tension. And this is a nice problem because you're just like imagining. No math, like just imagine like if they're being pulled outward or inward, and like it teaches you to just like envision it in your head, like with a little bit of a bend in each of the rods, which ones are being compressed and which ones are being stretched out. A bouncy ball is being thrown vertically upward from the ground. Air resistance is negligible, and the ball's collisions are perfectly elastic, which shows kinetic energy, which is energy minus potential energy. I think potential energy is U. Uh, so let's start by drawing potential energy. Potential energy is just proportional to the height. Potential energy goes like this. It's just bouncing over time. Now, but we're taking E minus U. So if I can sketch it, it'll be like kinetic energy will be just always total energy minus U. And you can see you get this sort of diagram. Um, I'll highlight it in green for our kinetic energy. And yep, it fits D. Okay, here's a fun problem. Uh, um, a block is basically a sliding down scale. What's the reading on the scale? First, we've got to assume that the scale only measures downward force. Forces to the left or to the right don't matter. Now, we'll take the block. We'll look at the forces. F, N, F, G. And together, if we put them together, they will make it accelerate down the path at like a 30-degree angle from the ground. F, N, F, G. Yeah, so FG is just G. It's MG, but I'll put MG because it requires an M in there. Now we can solve this. We know that this is 60 degrees, this is 90, this is 30, and MG, so trigonometry MG over 2 is here, and Fn is equal to mg root 3 over 2. So that's part 1 of the problem. Now we've got Fn is mg root 3 over 2, and it sort of goes down like this onto the wedge because they're equal and opposite forces. The force on the mass is equal and opposite to the force that it exerts on the block. Oh, and the block also has, wait. Oh yeah, the force on the block is equal to the force on the wedge. The wedge is massless, so we don't have to account for that. But this force is mg root 3 over 2. This is 60 degrees. Mg root 3 over 2. And to get to the downward force, the downward component of the force, which I'll highlight in green, we've got to do multiply by sine of 60, and we get mg times 3 over 4. And that's an answer. Pendulum is made with a string and a bucket full of water. When the string is vertical, the bottom of the bucket is near the ground. Then it's set swinging with a small amplitude, and it's leaking water. Okay, so the important thing to notice is that the amount of water dropped on the ground is proportional to the time spent at a certain location, which is proportional to 1 over the velocity, because the velocity is change in position over time. We're just looking at time, like per unit, time spent per unit, so it's proportional to 1 over v. Now, you might point out that it's technically the velocity, like, perpendicular, or I mean, like, parallel to the ground, because we don't actually care about the velocity perpendicular to the ground, and that's true. So 1 over v. Now, if you imagine when it's like at its furthest point, velocity equals 0, so the amount actually approaches infinity. And C is the only one that actually does that. The sides approach infinity like very quickly. Well, this is like linear, and these don't make sense. So the answer is C. Particle travels in a straight line. Okay. So let's draw v of x as a function of x ourselves. Let's say this is 2, this is 1, just so we can imagine it better. So if I've got 2 and 1, I want to know when it'll hit this velocity. Or actually, this will be like x naught and x naught over 2. So when will it hit this given velocity? Will it be before or after x naught over 2? Hmm. Will it be before or after the halfway point? Well, this point takes place before the halfway point in terms of distance, because you can see the distance traveled here is just the area of this triangle, which is less than 1/4 the area of this. I mean, it's equal to 1/4 the area of this overall triangle, which is less than like the halfway point. So we can put like the halfway point is here, and if we connect it, we'll get that it's sort of bowed outward. And we can do the same thing for here, for the right side. So we'll draw this point, we'll draw this, and we'll draw the halfway point. The halfway point is here. Now, on the distance versus time graph, will it be past the halfway point or before the halfway point? So the distance traveled here is more than halfway. It's actually 3/4 of the way, because we've got like this this portion is 3/4 of the overall triangle. Once again, it should be sort of bowed outward. And the halfway in terms of velocity occurs 3/4 of the way in terms of distance. Both sides are bowed out, so it's C. A rod of length L is sliding down a frictionless wall. Okay, so who had Mr. Kokoros in calculus? He had you do a lot of problems like this. X squared plus y squared equals L squared. 2x dx plus 2y dy equals 0. Just taking derivatives. We know that x and y are equal at the moment because it's a 45, 45, 90 triangle. So we'll just cancel out 2x with 2y. Dx equals negative dy. So we know that y has to be decreasing at the same time as x increases. So this also has velocity v. Another way to think about it is like a symmetry argument. If you ran time in reverse, the rod would be sort of going in the opposite direction at the same velocity. So it would have to have this velocity upward, like just by symmetry over here and here. So when you run time forward, the velocity has to be down. But I mean, I prefer the calculus method because it's just like cleaner and really easy. So the center of the rod is like the average of these 2 points. You can think about like it's the average of the x values, it's the average of the y values. So its velocity will just be the average of the 2 velocities. Here, let me add the 2 velocities. V, it's v this way, and tip to tail, v this way. So it's v root 2, but since it's the average, you've got to divide by 2, so it'll be v root 2 over 2, and that's b. Okay. Ooh, this is a great problem to just imagine potential energy, or not potential, kinetic energy. You actually see this problem a lot in F equals MAs. Okay, so it has a certain amount of energy, and with a coefficient of friction 0.8, it takes 100 meters to like do that much work in the other direction. And I'm thinking of it in terms of energy. So now 50 meters is dry, so I'll mark the 50-meter mark here. For the first 50 meters, it'll lose half of its energy because it's 0.8. For the next 50 meters, it'll only lose energy a quarter as fast because the coefficient of friction is a quarter as much. So actually, this final 50 meters only does a quarter as much. So you need like 4 times as much of the 0.2 coefficient of friction. So you'll need like 200 meters more of 0.2 because it's just a quarter as powerful. It does a quarter as much work per distance. And I'm using the formula that you should know that I'm using equals force equals, no, work equals force times distance. If you're doing a quarter as much force, then you gotta have 4 times as much distance. So overall, it's the first 50 plus 200 more meters, which is equal to 250 meters. Okay. This is tough. Okay, we're gonna use fictitious forces for this problem. The fictitious force pushing outwards is equal to omega squared r. Yeah, I think that's the formula. The forces pushing inwards are, let's look at the left spring first. If it's at a distance r, then it'll be k, like kx, but x is the displacement from equilibrium. So the displacement from equilibrium is r minus L. Similarly, this one, the displacement is, well, it's the same displacement from equilibrium, but now it's 2k because it has twice the spring constant, r minus L again, because the equilibrium is still at L. Now I'll just set them equal to each other. Oh, and fictitious force also has to be multiplied by mass. So m omega squared r equals 3k r minus L omega, or m omega squared r equals 3k r minus L. No, I'll move it to the left side. R times omega, or m omega squared minus 3k equals negative L. R equals, I'll just multiply both sides by a -1 to get this. R equals L over 3k minus wait, 3k minus 3kl. So this is plus 3kl. So R equals 3kl. I just noticed that the units weren't working out. So yeah, when I distributed this, I had to distribute the 3k to both. R equals 3kl over 3k minus m omega squared. And that's right here. And we've finished the first 10 problems. Let me just quickly check it. Yep, we got 10 out of 10. And that was fun.